This meeting is being recorded.
didn't give me the option of using BCC. I don't know why. So I apologize. If anybody's worried about me sharing their email, then let me know. And now let me share the screen.
If you want me to do anything today, you're going to have to make me a co-host. So
I don't know how to do that. So let's talk about that.
Go to the participant list.
Okay.
For my name, Ann Belegia, and then adjacent to my name.
Wait a minute. I'm not getting this. Okay. Your name, Ann. Okay, I see. Yes.
And then if you hover over, on my name, you should see an option for more over in the far right, which would, actually, I'm not seeing it. I was seeing it anyway.
Okay, I can make you a host. I can't make you a co-host.
Oh, really? Okay.
Well, you're just the host. You want to change the host to Ann Belegia. I don't know. No, I don't think I do. I can't make you a co-host though.
Okay. Well,
let's not worry about it now, Ann, but
okay. Maybe at the break we can.
I will I'd like you to run the questions perhaps.
Yeah, just people who are unmuted might want to mute so you don't have background noise. And then they unmute themselves when they want to talk.
So I'm going to go for about an hour. I'm starting at 7 minutes late. So, and we might run everything 7 minutes late. And then we'll take a short break and then we'll do questions. And I'm not sure exactly when my talk is, but I'm shooting for an hour. Okay, now I'm going to do share screen. And why isn't this? Oh, share. All right, and here we are. This looks good. Okay, here we are. And this is our second presentation, and we want to talk about energy in the natural world, the most important aspects of energy in the natural world, and starting from the evolution of even the universe briefly and the Earth. And these are some topics we're going to cover: the early Earth environment, the evolution of life, the particular role of the sun, volcanoes and meteorites, the importance of green plants, adaptations forced on life in an increasingly oxygenated environment, what I call the ecological theater and the evolutionary play. The ecological theater is the environment in which life lives, and the evolutionary play is the process by which evolution went forth, generating ultimately where we are now, and a bit about the evolution of increasingly biotic complexity. What are some of the main patterns that I learned as a biologist about what life was about? A brief history of our universe. And the vertical dimensions have something to do with size. And we don't really know what size means, but maybe. If you are pertinent, if you're skilled with the biggest telescopes and all, it does seem that the Earth goes back to what we call a Big Bang. And we don't know what was before the Big Bang, but it did seem like something happened I don't know how many billion years ago. Actually, I don't know, 4 or 8 or something like that billion years ago.
14.
And the Earth expanded enormously. I'm not the Earth, the universe expanded enormously, starting with hydrogen and helium, and then eventually they would recombine their neutrons and protons and electrons would increasingly combine to make the heavier metals, heavier materials. And all of this place in a matter of seconds to years, and ultimately generating, I guess here we have 13.82 billion years later, here we are, just remarkably, we're here, and we have the mental capacity to understand this, or at least we think we do. So, and then the next, on the left-hand side of your screen, is to give you some idea of the spatial dimensions of this. So the first one we see clusters of galaxies, and then within that a galaxy such as Milky Way, and then you can see the solar system where we are, each of them just being a billionth of a billionth or something of the size scale before. The universe is unimaginably huge. So I guess some of you, probably many of you, have heard that they took the giant Hubble telescope out in orbit and focused on an absolutely empty portion of the sky, according to the biggest telescopes we had on Earth. And then we took the much more sensitive Hubble telescope and pointed it at that hole in the sky, and the Hubble telescope found billions of galaxies, each containing billions of stars. So the universe is unimaginably large, and this leads statistical astronomers to assume that there are many solar systems, or something like solar systems, in this universe, and statistically within all of this enormous space, there must be a planet at the what's called Goldilocks, at not too hot and not too cold distance from a star such as ours, and that there must be life somewhere else in this enormous theater out there. But I can't say anything about that, and nobody knows for sure. But it's kind of humbled me as a scientist to realize how small we are in our solar system compared to the vastness out there. Okay, we're not going to talk about that anymore, but it's interesting background. Now, where did Earth come from? It's apparently an accretion of debris, rocks and dust and whoever knows what else, pulled together by gravitation some 4 billion years ago. And here's an artist's rendition of an early scene on Earth with a lot of volcanism, a lot of lightning, our asteroids crashing through the atmosphere, which is nothing like the atmosphere now, and probably had water fairly soon, although I find two views on that. And probably at one time, the Earth was smashed into by a Mars-sized blob that threw out the moon. The moon was once part of the Earth. I guess they think that when they bring back the moon samples. Anyway, this was a very, very inhospitable environment for any kind of life, certainly for ours. The early environment, the atmosphere was probably aerobic, very poisonous, probably a lot of lightning. And here what are some thoughts of what was in there: water vapor, carbon dioxide, carbon monoxide, hydrogen, nitrogen, ammonia. Now, notice there's nothing like free oxygen. It's a reduced environment, that there's no free oxygen like is 20% of the atmosphere now, and that we're dependent upon. And CO2 appears to have been very high, such as we can guess. And let's talk first. Now, I want to come back to that early Earth environment and tell you about what it was a really clever experiment. Now, there are three main sources of energy for Earth: radioactive decay, and in a certain sense, most of it comes from that. Geophysical, which means the hot middle of the Earth, which it's hot because of radioactive decay. And the sun, which is also a radioactive process. It's the sun is a fusion of hydrogen and helium of special forms fusion of hydrogen to generate helium. And with a little bit of mass that is lost, this generates the enormous energy coming out of the sun, apparently in accordance with Einstein's special equation, E equals mc squared. So a little bit of mass from hydrogen turning into helium in the sun generates an enormous amount of energy that eventually is the main source of energy in our daily situation in Earth. Now, here's a rendition of the sun, and the sun operates all kinds of things on Earth. In the past, people didn't have any idea how big the sun was or how far it was away. They could not sense this. They had no way of telling, although some early Italian scientists took some vertical wells and were able to get a pretty good size of the Earth and the distance of the sun from the angle of the sun rays going down vertical wells. Some very clever people were thinking about this way back when. Now, from our perspective, from a biologist's perspective, we can think of the universe as simply operating as free energy, i.e., the sun, going into low temperature gradient energy unavailable for work. Now, eventually, the universe, or our sun and the universe in general, supposedly will burn itself out. Now, don't worry about it. It's a very long time period till that is going to happen, but it has bothered many people that they call this the heat death of the universe, that it's not going to be here indefinitely. And from the laws of thermodynamics that we talked about last time, you can think about the free energy available, i.e. from the sun and other stars, running into low temperature gradient energy as it throws photons out into space. But Earth and the machinery of life, I put it as a little paddle wheel. I drew this back in 1975 or so when I was first thinking about these things. We would call this chlorophyll today, but life in various ways has exploited this dissipation of free energy, that is energy that can do work, into low gradient temperature. And in so it drives these gears, the machinery of life, in the process. So life doesn't have much to do with this process of running down free energy into heat. but it exploits it. And exploit is a word that I will use a lot. It doesn't necessarily mean a bad thing, humans exploiting other humans, that is bad, but the exploit means it simply uses that energy for its own purposes. Okay. Now, the main factors that have affected the solar energy budget on Earth: how much energy do we get and how much will we have? And the main processes are celestial mechanics, and we'll talk about each of these, Milankovitch cycles, and continental drift, and CO2. These are the main things that affect, as far as we know, how much energy is available for ecosystems and ourselves on the planet Earth. And there's a lot of complications to this, but we're just trying to take a look at the basic things. Now, it's interesting. Does my I don't know whether my view of you all gets in the way of my slides. But no. Anyway, they asked a bunch of Harvard graduates why the Earth was warmer in summer. This was at their graduation, and none of them could answer correctly. And it's kind of amazing to me how we don't teach these basic facts to undergraduates at our elite universities. But anyway, the reason it's warmer in the summer is because of the tilt of the Earth. Now, the Earth is at about 23 degrees to the vertical as it goes around the sun in an ellipse, according to the ideas we discussed earlier about how the solar system works, and Kepler's orbits around the sun. And in the winter, we're turned away. The northern hemisphere is turned away. And in the summer, it's the northern hemisphere is turned towards the sun. So obviously and here we are about the equinox, more or less, and it's about equal. But I used to teach in Argentina in December, and it was marvelous because I'd get late spring and then summer down in Argentina, and then come back here for spring. Okay, now the annual cycle was of critical importance to the ancients. And before they had brass, they built very large solar and stars and so forth observation devices, and they probably had multiple functions, but here's one, Stonehenge in England. And at certain times of the year, at December 21st, the sunlight will shine perfectly from point A to point B, and the priests could predict that they would do a ceremony to bring the sun back, and sure enough, on December 22nd or 3rd or 4th, the sun would start moving back to a warmer declination. So this gave the priest a great deal of power and enabled them to tell people when to plant and so forth, which is not like this year in Ashland is not always obvious from the observation of the temperature. We've had a cold spring, and but it's still time to plant. So anyway, this kind of information was found. The Temple of the Sun and the Temple of the Moon in Mexico, likewise, are giant astronomy observatories, which had to be large because you couldn't make precise instruments out of brass, or as we saw, as Tycho Brahe did, in just one house. So to get the precision that they needed, they had to make their instruments much larger. And there's a whole discipline of archaeoastronomy. And we find out amazing things that our ancient people knew so much. And for example, the Aztecs had built very sophisticated calendars that we barely understand. They had massive libraries, many thousands of books that were mostly destroyed by the conquistadors, who felt this was pagan rituals, and that were competing with Christianity or whatever. But it's taken us a long time. I think only one of the three remaining, I guess they call them codicils, or books that we have for those times, led us to understand that they had extremely sophisticated calendars back then and understood what was happening much better than any Europeans did until Kepler. I'm going to throw in jokes from time to time. Here's a couple of archaeologists looking at one of these ancient Mayan or Aztec, I don't know which calendars, and they say, best as I can decipher, it says we're all going over some kind of a cliff. And, we've got lots of computer models and so forth today indicating that we're going over some kind of a cliff. But in fact, in the case of the Mesoamericans, they did seem to their culture went over some kind of cliff. There's still plenty of Mayan genetic people in Central America, but we didn't realize until relatively recently that most of the hills in Central America, southern Mexico and northern Guatemala, et cetera, were enormous cities, much bigger than any cities in Europe at the time, that have been covered over by jungles. And I've been down there and looked over them, and it's just really, really amazing, beautiful cities at that one time, enormous ones. Now, here are some going on to things that affect how much sunlight or warmth a particular location on the Earth gets. Solar intensity, latitude, Milankovitch cycle, CO2. Okay, so let's look. The sun seems to be on a time span of interest to us, plus or minus not too much. The amount of energy coming out of plus or minus a few percent. Probably for most of the time humans have been on the Earth. And there are periodic storms on the sun that generate greater amounts of what we call photon flux density, solar intensity, from the sun, but we just get them. They sort of average out, at least there may be important storms for weeks or months, but they seem to average out over time. Just an amazing process. Now, a second thing that's been really important over the time span of interest to us at the moment in this lecture is, when I was a kid, it's sure, and we had a picture of South America, or of the world actually, on my 7th grade wall. I said, gee, South America fits into Africa just so neatly, and in fact it did. So a guy named Wegener, Alfred Wegener, back in 1900 or so, said, hey, look at these fit together. There must have been some previous connection amongst them. And he had further information in that there were fossils that would be found between South America and other continents. And here are various reptiles, a fern and the green one, and here's a Triassic land reptile, Listosaurus, a dinosaur. And the one, I don't know why they don't have it on this map, that interested me was Notophagus, the southern beach. And I spent a lot of time in Argentina and southern Argentina. And there were 5 or 6 species all over the place. But they're also found in southern Africa, in Australia. I don't know about other places than that. And, you know, I was studying this as a graduate student, and we had no idea that, in fact, the continents drifted, but we certainly had evidence that somehow they were connected. And in my courses on essentially biogeography, we would discuss these kinds of things. And it wasn't until maybe 40 years ago that some guys at Princeton put this together, some geologists. And as we got better and better, this is obviously a very recent, sophisticated view of the bottom of the ocean. We found these mid-oceanic ridges, and we were able to date the material as you would go away from the top of the ridges. And the ridges would be relatively young, sometimes just yesterday, and certainly just yesterday in geological time, and they got older and older as you got further apart. And so what we began to understand was that, yes, indeed, Wegener was right. The continents are drifting in many and complicated ways, and that this is responsible for all of the patterns that Alfred Wegener in 7th grade Charles Hall looked at on the maps. And here's a bigger view of the whole ocean. And you see the Pacific is, things are moving into the Pacific. And the possibility is that the moon was thrown out of the Pacific. Some people believe that. And the rest of the continents are adjusting to that deficit of mass in an orbiting planet. And this is part of what's causing the continental drift. Well, we do know that people wouldn't accept Wegener originally because they had no mechanism to move continents. But now we do, and it's these upwellings of lava in the middle of the ocean that pushes the surface away. Now, in Oregon and Washington and California, we're affected because the mass of the United States is being pushed towards the ocean, or probably more accurately, the ocean is diving under Oregon and generating the volcanoes that we see as part of that process. And so Oregon is moving towards Japan at, I don't know, a very slow rate, but it's happening. And ultimately, this generates earthquakes. I don't think we're in a particularly dangerous zone here, but Seattle is, and San Francisco is. And so all of these plate tectonic movements change how things are. And you notice that the drier areas, it's a little more complicated than I'm saying, but the drier areas tend to be located in the middle of large land masses. And we'll talk about this in a minute, but the continental drift generates different areas that are closer to and further from the ocean, and the ocean is the source of most of the moisture that drops on the land. So the green areas on the map are heavily vegetated, and the light areas are deserts or near or grassland sometimes in the middle of large land masses. Now, the idea is that magma is coming up from underneath and pushing the surface of the earth and the new material outward. And this is the mechanism that Wegener was unaware of. And these are large, when I said three main energy sources of the earth, and one of which was geological. Here's one of the geological energy sources doing its thing on the earth. And here are different pictures of the land mass from 225 million years ago to 150 million years ago to 65 to nowadays. And you'll see on the back of my red Prius a bumper sticker that says "Reunite Gondwana Land," and you will be now sophisticated enough, I hope, to understand that it's a joke. It sounds like a political statement, but Gondwana Land is this big mass in the middle here of ancient continents, and so Reunite Gondwana Land is a joke. Okay, now this guy Alfred Wegener, I'm sorry, Milutin Milankovitch, he got obsessed with the cause of the ice ages, and he felt it was due to the processes of how the earth went around the sun. So, and they had different, if you look at a top spinning, and as it slows down, it begins to wobble. Well, the earth was set into motion, whatever, 4 or 8 billion years ago, and I guess 8, and but it precesses, it changes as it slows down, and just like a top does, kids toy top. And so he found that there was what he called precession, the movement of the pole from where we see it now to some other place here off of north of Alaska, I guess. That's called precession. That has a cycle of 26,000 miles. And the obliqueness, that is the angle from the vertical, would change from 22.1 to 24.5 at a cycle of 41,000 miles, and the eccentricity, which Kepler talked about, it would become more and less eccentric over a period of 100,000 miles. And he thought this was probably responsible for the coming and going of the ice ages. So
I think
he
you mean
was
years.
from Central Europe, and it was obvious that at some point this had all been covered with glaciers, and so he was interested. He was obsessed with this, and mathematicians have loved it because you can use sine waves and so forth to deal with these things over long times of periods of time, and they could, I guess they can pretty much predict the coming and going of ice ages. I don't know exactly where we are and how accurate Milankovitch is these days. Now, CO2 doesn't affect particularly the amount of sunlight entering the Earth's atmosphere, but it's obviously very important for the temperature. And Tyndale did some experiments in England in the 1850s or so, where he took a tube a meter long and shone a light through it, different wavelengths, and found that the certain wavelengths would were absorbed by the gas in the tube, and that CO2 was especially important. So he figured this out way back in 1850 or so, that the Earth was probably kept warm, and we now understand that the Earth is about 30 degrees centigrade warmer than it would be if we had no atmosphere. In other words, it's really important that we have CO2 in the atmosphere, because, or else all water would be frozen. We'd be in an ice age all the time. Now, they've undone what are called paleo temperatures. Oh, you can understand paleo CO2, the paleo meaning old. They drill down through big glaciers, such as Camp Century, Greenland was a famous one. They take an ice core going way down, and then they're going back in time as they go down deeper into the core. And then they'll take slices back in the laboratory. They'll keep them frozen, very frozen, take them back to the laboratory at Ohio State. They had a terrific laboratory for doing all this. And Lonnie, somebody was doing this really magnificent science. And you could slice it and smash it with a special hammer and release the gas that was caught in the ice and get what are called paleo CO2 concentrations. You can look at what the bubbles in the ice were going way back in time, and you can get temperatures, paleo temperatures, from the ratio of 016 to 018 isotopes of oxygen. And when you do that, you find that for the last 800,000 years, there seems to be a pretty good correlation with of the temperatures, paleo temperature, paleo CO2. Somebody has their mic on, and please shut it off. And so, and you look at that and you say, oh, wow, we're screwed, because look where the CO2 is now, and the Earth has not experienced that, and that's a terrible thing. But if you take a longer view, this is the same data I just showed you in the current level, but you take a longer view of CO2, and here is where we are now, the red line. The blue is the pre-industrial CO2 level. But for most of Earth's history, at least over 500 million years, the CO2 has been higher than now. And so what does that mean? Does that mean that, in fact, we're protected from the CO2 because we've been there before? Or we've been 4 times higher in the past, in times Triassic and Jurassic, when life was doing very well. So we don't really know this. We don't really know this. Oh, this is supposed to be a joke. It didn't. Now that we've achieved net zero, what do we do now? So that's just a view of where we might be to achieve net zero. Okay, about 4 billion years ago, something truly big happened, and it's called life. And how did life originate? First hypothesis is Charles Darwin and all of that. And the second hypothesis is divine intervention. These are still competing worldviews out there. And the argument in favor of natural selection, which obviously is completely my perspective, is if there exists variation within a population, now look on this group of people, there is variation amongst us. And if these variations is to some degree heritable, and most of us look more like our parents than probably parents other people picked at random. And third, if there is differential survival and or reproduction among these variations, natural selection must occur. Now, that's something that has to be understood by those who question evolution. You have to say which of these three things is not true, because the logic leads you inevitably to natural selection must occur. And I certainly don't want to question anybody's religious sensitivities, but for one to question Darwinianism today with the massive amount of information that's totally consistent with it, and to me is rather amazing thing. So let's think about the earliest forms of life. The earliest forms of life were microscopic, that left signs of their presence 3.7 billion years ago. And these are in called stromatolites or something like that in Australia, big bays of these things. But when life, I don't know, apparently we're not originally photosynthetic, and it's not quite clear to me what energy sources it worked on. But photosynthetic blue-green algae evolved some 2.4 billion years ago, and they used the sun's energy to generate energy-rich reduced compounds from water and carbon dioxide. So blue-green algae looks kind of like this. It's around here today. You can see it sometimes today. This is mixed in with some less quote-unquote primitive material, but let's not worry about it. But the equation is water plus CO2 in the presence of sunlight and chlorophyll generates sugars and oxygen. And what this meant was, for the first time, the Earth's atmosphere became oxygenated. And so you can see this, it made all kinds of difference. This is a rock I picked out of a stream in Glacier National Park. Now, in Glacier National Park, you see these grayish green rocks all over the place individually, and these reddish rocks that look like they're the same material all over the place. But what happened here was in the interval between the gray rocks and the red rocks was the evolution of photosynthesis in an oxygenated environment. And these are iron-rich rocks, and they rusted. So this is red because of iron oxide, rust, which would have been in these rocks, except the atmosphere had no oxygen. So it had a tremendous change over all of Earth. And originally, oxygen was extremely toxic because it attacked all organic compounds. And so organisms had to evolve skins and isolating mechanisms for food, and such as guts and so forth, to and mitochondria, which are probably once free living flagellates that are used to use the oxygen. Life evolved to use the oxygen to utilize organic compounds more efficiently. Okay. And here's a view of the early Cambrian, that's a geological time, life, all kinds of really strange eurypterids and other kinds of creatures that don't exist now. And here's a so-called spiral of life. Not quite sure why it's a spiral, but anyway, time goes up on your screen, and the Cambrian or Ordovician, Silurian, Devonian, and for example, this is the age of fishes, and Mississippian and Pennsylvanian when all the carbon was put down, and Permian and so forth. All of these geological times and life and the planet changed. It's just an amazing story. It was just fantastic for me to take geology when I was young. Now, periodically, something happens to reset the clock. And back here, somewhere around the end of the Cretaceous, for example, there was a big one, something, probably a giant meteor smashing into Yucatan. And it killed out all the dinosaurs and made the situation, all the dinosaurs except for birds. Birds are modern dinosaurs. Look at their feet, they're scaly. And the ancient mammals at that time came along, and here we are. So these big things that would happen would reset the clock and life would adapt. And a lot of people are arguing that what humans are doing to the earth now is resetting the clock, but I'm sure life will evolve something else, and maybe the dolphins will take over, who knows. So from this beginning, I hope you can see my cursor of archaeobacteria. Archaeo means old bacteria and so forth in the sort of lower 1/4 middle. They evolved all these plants and animals and fungi and all kinds of other creatures over time, and different ones would come out from time to time, and you have to follow here. Vertebrates come out of here, and you follow them around here. I don't know quite how you get here, but you get the birds, reptiles and birds, and owls and rabbits and primates, including ourselves, and felines and hippos and badgers and whatever else. Just an amazing process. And here's another way of looking at it a little bit simpler. And we used to put humans kind of near the top. And here's a perspective. This is a summary of this lecture in a way. Just think, Earth has a cloud of dust 4.5 billion years ago, and then all this stuff came along, and finally, a million years ago, man, or humans, and then there's me. This is Calvin and Hobbes. I don't know. Biologists love Calvin and Hobbes, and they love Gary Larson. So you'll see those cartoons from time to time. Well, that's not true, because there are all kinds of pathogens that can only live in humans and hence have to evolve since humans came along. So we are not the latest product of evolution. We're just another one in that giant mix. But we have the capacity of understanding these things, which is amazing. Now, there's another big thing the sun does that I'm going to talk about in more detail next time, but the sun drives at the equator. This is a globe, portion of a globe, what are called Hadley cells. It lifts water up at the equator and drops a lot of water here. And when that water comes down at north and south, then it makes deserts. And those are the dry areas I pointed out earlier. And it also generates the winds, and we'll talk about how that happens next time. But the Earth is a giant heat engine driven by the sun. And all kinds of things besides photosynthesis, but including our weather patterns and the distribution of life, depend upon the interaction of these wind patterns and moisture and the patterns of heat derived from the sun. So we have tropical rainforests where it rains a lot near the equator, for example. We have deserts where at 30 degrees north and south, where the descending air masses suck the moisture out of the earth. In between, we have savannas, which are a little bit of each, or seasonal forests. There's a glacier on the top of Mount Kenya on the equator. And we have boreal forests to the north. Second largest biome on Earth is this taiga or boreal forest, each of which are responding to the solar-driven patterns of moisture and temperature. Okay, now I'm going to talk about ecology, which is my field, and the historical development of what trophic means food. That's all. It just means food. And so this guy Tansley came up with the ecosystem. I'm an ecosystem sort of ecologist, not individual species organism ecologist, more or less. And he used it to find a unit that covers all organisms of a given area as well as their inorganic environment. And then George Evelyn Hutchison, who was my academic grandfather, contributed a lot to thinking about ecosystems, and also to those who decried the value of studying ecosystems. Lindemann in 1940 came up with what's called the trophic dynamic concept, meaning the dynamics of food distribution in an ecosystem. And he died just after he was dying while he was doing his beautiful doctoral work on this lake here in Minnesota, and following the flow of energy from the sun to the plants to the small copepods and animals to the small fish to the big pike in the water, the whole food chain process, and finding only that about 10% of the energy was moved from each trophic level to the next. And here are the main things that he said. Ecosystems could be conceptualized as trophic assemblages. Energy flowed from the sun to primary producers, meaning plants, to herbivores, to a series of carnivores. Transfer of energy was roughly 10% at each level. And trophic efficiency appeared to increase with trophic level. That's not held up too well over time. And my advisor, Howard Odom, also worked out, measured these things for the first time, came up with a series of very clever procedures for measuring how much energy was used by entire ecosystems as well as their components. And I'm going to give you you can measure the energy flow. You can just see how much carbon is captured or energy is captured by a plant, or you can look at gas exchanges. This is for Spartina grass in coastal environments. And this, I've done a lot of this stuff in my life. And I devised this procedure for getting a quadrat, meaning a square, how much stuff. There's this quadrat of grass production, and so here's a quadrat of fish. So I devised this procedure, got a lot of data in estuaries that way. Okay, now I'm going to end. I guess I've got another few minutes because in about enough time to do this quickly, to show you how we actually go out and did this. When I taught my systems ecology class was about building models of ecosystems, we would start by going out to an actual ecosystem. This is Little Sandy Creek in upstate New York, north of Syracuse an hour, going into Lake Ontario. And I would take a class out there and have a very organized assault on this ecosystem, measuring how you did it. And I think Paul did one of the first of these. We became much more organized over time. So here's this beautiful little stream flowing down out of the woods and through a pasture. And the students would come up for the whole weekend and camp out. And so there'd be 2 or 3 times as many tents by the time they were all in there. And the logistics would be very complicated. We'd bring up many trucks full of equipment to organize our field trips. And I did this, I think I did this pretty close to 40 times.
Oh, my golly.
Exhausted. And people are here figuring out, we're going to show you later, this box in the foreground with a net is how you sample insects. So I'm going to show you how you go about measuring energy flow in a stream. If you look on the back table, you'll see quite a lot of chemistry equipment as well. Now, we'd set it up as a military situation. I was General Hall, and this is, for example, over on the left, Lieutenant Omar of the fish group, and we'd have a lieutenant for each of the major components that we'd measure. And we'd start off Friday night with a soliloquy in which I would explain systems principles, whole system analysis or analysis of the pieces of all of the system. That's ESF, meaning environmental science and forestry, the marvelous college or university where I taught later in life. And so I also would show them how to take a Winkler. A Winkler is a device for measuring oxygen in water, and the chemistry by which you would titrate the sample. And the first thing you had to do was measure the physical properties. In this case, this wife took this the first year we were married. It almost ended our marriage. So this is my wife chasing a lemon down the stream to see how fast the water was going. That's a quick and dirty way of measuring water flow. And we'd also measure the dimensions of the stream as you'd go down. And here we got more sophisticated water flow measuring devices in time, but you'd stretch a meter tape across the water and take a meter stick and get the depth, so you measure the physical dimensions of this. And then we were on this beautiful, beautiful piece of land that the landowner was very happy for us to use. And so the students are going off to sample oxygen and insects at some far reach of the stream. And the students would go out every 3 hours at 3 places in the stream and measure the oxygen of the water. So that's a Winkler bottle. And you fill it carefully and you put in these chemicals, and eventually you get something that looks like gasoline, which you titrate, and you can tell the oxygen in the water. And we do hundreds of these over the course of this experiment, and we do it at night. And also, this is a microscope looking at insects that were captured at night. And we'd have what are called benthic chambers for taking a little section of the stream. See the algae on it. That golden algae runs the whole stream, runs the bugs, runs the crayfish, runs the trout, runs the big salmon or little salmon that are in there, since it was a salmon nursery. All of this was done. And then here's another benthic chamber here. And here's one of the stonefly, I guess. That's insects. There are lots and lots of insects in the stream, which these young ladies would get from their benthic sampler, that square box on the bottom. And then we'd block off a section of the stream. You can see that section of the stream behind the students there, and there'd be another net out of the picture. And then we take an electric, and there you see right there, they're measuring probably a rainbow trout on how big it is. And we'd use a shocker with some very sophisticated math to find out how many fish there were in the stream. and again, weigh them all and stop for lunch. This is Jerry Mead, who was my TA many times, a magnificent stream biologist. And you take the individual fish, and here you have a brown trout and a hogsucker and so forth, and you put them in one at a time into a chamber like this. We'd use these hold devices, these mice chests, and put some plastic on the top so there would be no exchange of oxygen with the surface, and find out how rapidly each of them would use oxygen, which would tell us how much energy they were using. Each organism. We did this with bugs, we did it with fish, and we even published it. And I'll put this on my site once I figure out how to do it. And so I'm trying to put everything onto a Dropbox site, which I haven't quite figured out yet. And you come up with an energy flow diagram of the energy as it comes from the algae on the water, less and less energy being used as you go down, and a lot of energy coming in from the trees, in being used by different types of organisms, and we'd summarize all this and publish it. We also did this, let's see, I got 2 more minutes, I can do it. We have great new tools. You can just clamp this thing on a leaf and measure its rate of using energy by its change in CO2. We'll talk later about the maximum power hypothesis, but we tried measuring this, that there was a trade-off of rate and efficiency in the tropical forest. So we went down in Puerto Rico, and we first of all, we'd shoot a slingshot with a fishing weight with a fishing line attached to it over to a top limb of these big tropical trees. And this is Nancy Harris's PhD work, and magnificent work. And then she'd go up with rock climbing equipment to the top of the trees and everywhere up and down the tree. And with that device, measure the rate and the efficiency of photosynthesis of the whole ecosystem. Very complicated study. And we found out that it seemed to support the maximum power hypothesis, which we will talk about later. So this is just showing you how we used various techniques in the field for measuring the rate at which life uses energy. And we can do that also for entire civilizations. But we started by thinking about it from how it operated in an ecosystem. Now, I think I've used up my 1 hour, so we'll take a 5-minute break. And then we'll come back, and I hope you're going to have some questions. And I'll get out of my screen share so we can all see each other, and everybody, please come up with a question. Okay. Yes.
There are several people who are in the same physical space who have their devices unmuted. And that's what's causing a lot of feedback. And I've been trying to chat with you to tell you to please turn your sound off, because it's going to be.
Please turn your sound off unless you're speaking. It causes the rumbling in the background. Okay, so I'm going to, let's see, how do I stop my screen sharing? And see you in 5 minutes. And we'll have half an hour of questions. Okay. Screen sharing, stop share. Oh, there we go. Okay, there we are. No, I had some trouble at the beginning. And I'll tell you about it later, but right now it's just my 5-minute break and.
I want to say how meaningful that those experiments were. You know, they were fun in many ways, but you know, there weren't many other classes where we went out in the field for a weekend or several days and had to build our own equipment. I remember making a plexiglass box to put fish in. And, yeah, it was it really changed, you know, the way I thought about systems. And
Well, I think it was really useful, Paul, because when you did it, I don't think I was teaching. Did you take my systems ecology when we went to 6 Mile Creek or?
no, this was
Fall Creek.
We went to Fall Creek. Yeah.
So you went on that weekend trip to Fall Creek.
That's right. And
Oh yeah.
I think it was limnology, maybe, or something. But
I don't. I think I taught the full systems ecology my last year or two at Cornell.
okay.
And when we went down and, you know, we took our tents and we hiked way the hell up in the gorge and I made a big mistake. I learned out something really important then is don't let the students go until they've carried the equipment out. Because myself and Chris McGoy had to carry most of the equipment out and it was a real hike. But that was a marvelous field trip. The weather was wonderful. Ed Brothers, remember, came along.
Yeah.
My friend Ed Brothers and did the fish stuff. And my dog Molly was there and fishing the whole time. Yes, that was a wonderful experience that day. And all the other times I did it at ESF, I really got into doing it big time. And then we build models. I don't know whether you were part of that time.
Well, that was my first introduction to computer modeling.
Yeah.
And we had to do it on before they had terminals around. You know, we had to put them on cards and stuff, as I recall.
Yeah. Oh, God. Yep. Yeah. Okay, here we are back. And so raise your hand. Ann, are you raising your hand? You turn on your microphone when you want to talk. Paul, turn yours off now.
I'm just going to ask that Lynn and William turn their sound off. I believe that's where the feedback is coming from. I see William's out of the room. I don't know where Lynn is, but when you're in the same household and you both have your sound on, you get feedback. So I don't know. So I can see that neither one of them is physically present. I'm sending chats to them, but they're not turning off.
Yeah. I'm wanting to get pretty clean. This is kind of my swan song, this class. And I want to be able to have nice presentations that I can leave for anybody who's interested in these topics in the future. So, okay, anybody else have a question? Ray?
Okay, Charles, just a comment on the CO2 level chart that you had.
Yeah,
Yes, the Earth has been at higher CO2 levels than we're currently at. However, I believe those were hothouse states, which were quite
Yes.
different for temperature, which is why you find some of those fossils in Antarctica. So I think it's going to be difficult for our human civilization to exist.
oh, I'm
at
not
those
saying there's anything
temperatures.
good about it for us. But,
Okay.
you know, the different cultures of different ecosystems and different species and different cultures of humans, such as the Mayans, come and go. And the CO2 might have a lot to say about where the future goes. Certainly many people think that. I have a slightly different view, but only a little bit different. I respect the fact that we're really tinkering with some very dangerous stuff with the changing of the CO2. Incidentally, I think, did you all get on from linking to the original link to this class? And did that work? Anne is saying yes. And so
Yes.
from now on, we will try to link to this class from the original link, which I will send around again. And I'm also trying to set up a Dropbox so that you can get the material, a recording of the class, or look at the PowerPoint again if you want, and I will be putting some reading material on. Paul Kemp, could you see the PowerPoint from my screen? I can't hear you. I can't hear. Your microphone, Paul. No?
Okay, I can't see the PowerPoint yet. I have two
Really?
screens available, but
Did you get the one I sent you?
oh, yeah, I got that. So
Well,
I
you
should
could have
just
opened it
follow
and
along with that, I guess.
I don't know why it doesn't work, whether the Pony Express doesn't go between Oregon and Louisiana anymore or whatever. But
Well, undoubtedly, it's something I'm doing wrong.
I don't know what it would be.
Paul, maybe you and I can chat offline.
Okay. Appreciate it.
Okay. All right, questions?
So
Yes.
how do you put error bars around these measurements?
They're big. And but the difference is, the interesting thing, Paul, is usually the difference between the lower trophic levels, an herbivore, say, and the upper trophic level, maybe one of your big birds that you like so much. The quantity of biomass is so different between the plants and the herbivores and the carnivores that even if there are error bars of 50%, there are order of magnitude differences between them. So relatively speaking, the error bars, which we've dealt with from time to time in the past, are not quite so bad. And what you try to do is if you do your measurements right and you have enough dedicated people, you can do that. then you can measure these things pretty carefully. I think. I mean, come on, if I asked you for certain species of birds in southern Louisiana, you could probably tell me how many there are per hectare, plus or minus something or another, right? Well, you get a lot of birders to work, and you can get good data.
Yeah.
Just takes manpower and
Yeah.
person power. Marianne, did you have your hand up?
Can you hear me?
Yeah.
What did you say?
Did you have your hand up?
Yes, I did. I just wanted to tell you that there is so much reverberation that I really want to, I really want to hear what you have to say, but there's so much reverberation that I can't, it's hard to hear. It's hard to hear. Is anybody
That's
else?
because people have their microphones open, I think.
Marianne, it might be, I see you're logged in twice.
You
And at
think
one
what?
point, I think you were not muted, so you were probably causing some of that feedback with having two microphones in the same position.
No, I think it was William and Lynn,
Okay.
that they're in the same, I believe, William, you're here now. Are you guys in the same physical space?
Can you hear me?
Yes.
Okay, well, Lynn,
Or you have two devices on.
everything was in Lynn's name for years. And today I saw a place where I could put my name in, so I did. She's not here.
Well,
It's just one computer.
oh, it's weird because I'm seeing two different, well, anyway, I don't want to take up the question time.
Marianne, would you
There are
like
two
me
pictures
to?
of me and I have no idea why.
But
Yeah,
I haven't said a word, so it's not my voice.
Well, your microphone was on and now it's showing as Lynn's microphone being on. I don't know. We can talk about that later, but
Lynn isn't here. There's only one computer.
okay. All right. Well, I don't want to take up time for questions with this.
Marianne, would you
Yes.
like me to send you the recording? Would you like me to send you the recording and see if that's any better for you?
That would be wonderful.
Okay, I'll do that. Okay. Let me write myself a note.
And I might be able to fix some of the reverb if you send me the MP4 file.
Okay. Now, I'm a little disappointed in this class fight. It's your class too. You have to be involved. You have to ask me questions, or I'm sitting here feeling a little bit embarrassed. So let's hear some questions. Surely all that material, there must be something you have questions about.
Well,
Go ahead.
yeah,
Well-
I guess you were talking about the Hubble telescope, and
Yeah.
I think the one that
Webb.
they have now, the Webb telescope, can see well beyond anything the Hubble could, and
7 times further,
yeah,
or more something.
but they still can't see the edge of the universe,
I
and they
know.
think it might be older than 13.8 billion years.
Well,
No, I mean,
whatever it is, it's going to be astonishing. And
Yeah.
I don't understand when Einstein's concept of light bending in around. I mean, there's supposed to be some limit to the universe.
Yeah.
That has to do with Einstein's. If anybody knows about this, raise your hand. Cassie?
I don't know about that, but I had a question regarding your fish and ecological studies and measurements.
Yeah.
Have you done any of that in the Pacific Northwest?
Salmon, yes. Write this down. www.bpe
Yeah,
Institute. That means Biophysical Economics Institute.
Okay.
Go to the bottom of page 2.
Mm-hmm.
And if you want more, I'll send you more.
Oh, okay.
So the
BPE
answer, BPE,
Institute.org.
BPE Institute, one word, www.bpeinstitute.org.
Right. Bottom of
Okay.
page 2.
Yeah.
Thank
Well, you can
you.
look at page 1 too, if you want, but
I'll look at all of them.
all right, it's about birds. So the page 2 is fish at the bottom.
Great. Thank you.
Well, obviously, when we start talking about civilization, modern contemporary civilization and economics, it will all be applicable at your local grocery store or whatever. So it, it will, and these kinds of food chains, I haven't done them, I haven't measured them, but other people have in the Pacific Northwest. So we have some idea for what these numbers are for Washington State and, I don't know, Mount St. Helens region and so forth. They've been measured there. And there's a Sage Hen Creek fish station in California, not too far from here, where they've at least done a pretty thorough job on the fish. I'm not sure about the whole ecosystem. So I mean, as a fisherman, as a kid and a 20-year-old and so forth, I'd be so focused on the fish, but then I'd go and measure the ecosystems, I'd find out that the fish were not even 1% of what was going on in the stream. Most of the energy activity in the stream was in the algae and the microbes and the plants and even more the fish, more the bugs than the fish. And I didn't understand this until I met Odom and began to understand ecology this way.
But our interest is often not, yeah. We have to,
Yeah. We're a top carnivore.
It's we're consumers like the fish are. They're consumers. They're not producers.
Yeah, I don't think the pike cares about the algae. He cares about the perch.
Yeah, Charles, I hope to have more questions later, but still getting some understanding of your theory of energy and biological systems. So
It isn't
we'll see
a
how that goes.
theory. It's a way of thinking about the system. Is it a theory? I mean, you've actually caught me a little bit off guard there.
Okay.
It's a way of thinking about things, because in the first thing, when I look at a pile of dishes, I think about the energy required to clean them. Not just my energy, but the energy from fossil fuels and from my own energy and from embodied in the soap and so forth. And when I go to a grocery store, I ask, how did that apple get there? And what's required to do that? And so I look at a consumer product. Somebody sent me an interesting email. I guess Anne sent me an interesting email saying, should she go get in her car and go and pick up a number of widgets? Widgets is a generic term for something that she purchases, or should she felt guilty when the UPS truck came. But I said, the UPS truck probably in the same distance you would travel to pick up your 2 or 3 widgets has serviced 100 different customers. So I think it's probably, I mean, I'd have to do the math, but probably you're way ahead, Ann, by having the UPS truck or the postal service, which is going to come there anyway, deliver your whatever it is that you want. So these can be translated, can be thought about in a day-to-day basis.
Well, I think your point is maybe you don't consume so much. That's another way to address that.
Well, you know, I live in an affluent town in a nice house, and although I have a Prius, I also have a 4Runner for when I want to go backcountry fishing. So there you have it. But the only thing I did, I guess I told you this, the only thing I did that was eco-virtuous in that sense was at age 20 something, I chose not to breed. Because I figured that would be the largest impact. And nobody talks about that, but that's the largest impact of all of us, is when we choose to breed. Now, I'm not saying that you shouldn't breed at all. I'm not saying that at all, but it's something to think about.
Well, the other thing to think about is all the stuff you have, which we are not immortal. Where is it going to go?
Right. Who wants my library? I mean, universities don't want libraries anymore. Anybody connected with Southern Oregon University, they want some energy books. What happens when I die?
Oh, I do have a solution for that. Rogue Metaphysical Library will take any book, and they will, I mean, we took 18 boxes of books to them when we downsized.
Yeah, but I
and,
want somebody who will appreciate the books.
well, they'll find a
Maybe
home.
one of you, I don't know. How about my opera collection? Who listens to opera on vinyl anymore? Me.
Hmm.
Okay, come on, let's hear from some more of you.
Well, what do you think are some of the, we have these factors of the CO2 going up and the things happening with the sun and volcanism and continental drift. And there's some things that happen gradually, and then there's some things that happen catastrophically. And, it's hard to model, I would think, some of these things in terms of
Oh, I don't think we can model our future. I mean, an asteroid, I mean, I guess they're looking for them now, but an asteroid like the one that did in the dinosaurs could come in tomorrow, I suppose. And big volcanoes, I guess they're trying to predict them, but look at Eastern Washington. I mean, it's just covered with hundreds of meters of volcanic stuff. And what was that all about? I mean, and the main thing about volcanoes is that their impact is not on the lava, but the stuff they throw up into the stratosphere that blocks the sunlight. And so that's what we have to, if we're going to be worried. But you ask, can we predict these things? Can we make a computer model of them? And the answer is probably not. But I don't worry about asteroids and volcanoes tomorrow because they're too rare. They're statistically so incredibly unlikely. But what I do think is the most difficult thing to model and the most dangerous of all of these are social issues that we can't predict. And they can be pretty serious. Yes, Cassie.
So what's on your agenda for next week? I want a sneak peek.
Think early humans. And how did early humans get there? And how did they deal with their own energy requirements over time? So that's sort of the sort of the basic topic. Okay, is this going okay? Any suggestions or feedback, or if you have some, you can email me anything you want. And this is your class. And we'll see you next week. And I guess the original link, which I will send out again, is what we should do so we don't get messed up. As I did today. Maybe some of you did. Okay?
Thanks, Charles.
Thank you.